All right, we've been talking a lot about the rate of chemical reaction, rates of chemical reactions, and we have what we call now a rate law. And we can write a skeleton rate law, and we've also practiced filling in the different components of the rate law, okay? So we're asked here, this is a little review for us now, and also some exercises, because this is the kind of stuff we're going to be doing on tests, exams, right, and quizzes, is determine the rate law from the given data. Okay, so here's a chemical reaction. What do you think? What is the rate law going to look like?
Well, I know the skeleton rate law looks like rate equals K times concentration of reactants raised to exponents.
Very good. So let's write that down. The rate equals lowercase k times the concentration of what are our reactants here?
Looks like B and C.
Okay, A, B, and C, and I'll raise those to X, Y, and Z. Okay, so there is our generic rate law. Now, how do I go about identifying what X, Y, and Z equal to and what K equals to?
So let's see. You choose two reactions, like the first line and the second line.
Okay, so we're choosing two experiments, the first one here and the second one here. And it's nice to choose two experiments in which nothing changes except for one thing. All right? And when we do that, then we can see the impact of the rate by that one reactant. Okay? So in between first and second reactions here, these first and second experiments, what changes?
The concentration of A. It doubles.
Very good. And that's it. Nothing else changes. So when we double the concentration of A, what does the rate do?
It doubles as well.
Very good. So what does that mean the exponent on A would be?
0?
No.
Oh, 2.
No, not 2. Let's take a look at this a little bit closer here. So let's, again, I prefer to, instead of writing in these values for rate, just write in numbers that kind of represent them. So if we said that the rate for the first reaction here is 1, then the rate for the second is twice as fast, right? The concentration for the first one of A, let's say that's 1, and let's say all of these are 1. Then the concentration for the second one is 2, 1, and 1, right? And now, again, X, Y, Z, Z, Y, and X. K is going to be the same number for both of those. So we can identify what the exponent on X is here. You said 0. If it was 0, then the rate would not change. If it was 1 here, or so you said 2, if it was 2 here, 1 to the 2 would be equal to 1, 2 to the 2 would equal to 4.
Oh, so it's just 1.
That's right. 2 to the 1 is going to be 2, and that's going to double the rate. Okay, good. So we've learned that the order of the reaction with respect to A is what?
1?
That's right. It's 1, or first order. First order. And you can say 0 order, first order, second order, depending on that exponent. All right, good. So now we see that the A is to the 1. Now what about B or C?
Well, let's see. If we compare the first to the third reaction?
Very good. So here's the first reaction to the third reaction. Now why did you choose those two?
Because nothing's changing except for B. Only one thing's changing.
That's right. And that's what we want to do. If we were to choose the second to the third reaction, we have A changing and B changing. And then the rate change would be appropriate. And we do have the exponent for A, so we could figure it out. But it's just simpler when we choose two reactions, in this case the first one and the third one, two experiments where only one thing changes. And what happens when we double that rate? How does the rate, double that concentration of B? How does the rate change?
It doubles as well.
All right. So then what does that mean the exponent on B is?
That was, let's see, doubled. It's like, it's going to be 1, right?
That's right. It's 1. Just like the B, or just like the A, when you double it, that means the exponent, if the rate doubles, that means the exponent is 1. Same thing for B. All right, now what two reactions can help us out with C?
The first one and the fourth one?
The first one and the fourth one? That's right, because the concentration of A is the same, concentration of B is the same, concentration of C doubles. So what do we see? When we double the concentration of C, how does the rate change?
It doesn't change.
That's right, it doesn't change. So that means regardless of the amount of C that you put into this, the rate doesn't increase any. And so that tells us that the rate with respect to C, and you could do this again, but you would see that it has to be 0. It's always 1. It doesn't change the rate. All right, so then we have rate equals K, A to the first order, B first order as well, C to the 0 order. Okay? And then, and this is algebraically comparing them, then we have our rate law, A, the concentration, or to the exponent 1, B to the 1, that's what I have written down here. They don't include C on here, right? You don't need to include C because anything to the 0 is 1. Now, how do I find K?
Oh, now we just take any, does it matter which one I take?
No, it shouldn't matter which one you take.
So we just take any reaction. I'll choose the first one. And then you put in 0.1 for A, 0.01 for A, 0.02 for B, and set that rate equal to 0.0002 and solve for K.
That's right. Very good. So if I put in here 0.01 for A to the 1, B 0.02 to the 1, C to the 0, I'm not going to include that there, rate 0.0002, I can solve for K now. So again, this is all the information from a single experiment, in this case the first experiment. And so I got 0.01 times 0.02, and that equals 2 times 10 to the minus 4. So that shows that K equals what?
Is that 1?
That's right. So 0.0002 divided by our answer here, and we see that K is 1. So the rate law is the rate of the reaction will be 1 times 0.01. No, that's made a mistake. Start over. The rate of the reaction will be 1, that's my K, concentration of A to the 1, concentration of B to the 1. So you tell me the concentration of A and concentration of B, I have the K value, and I can always tell you the rate. And that's what the rate law provides for us. Now, let's look at the units for the K value. The units for this is molar. The units for this is molar. They're all to the 1. The unit for the rate, what's the unit for the rate?
That's molar per second.
Very good, molar per second. So what does this have to be? So that something times molar squared will equal molar per second.
1 over molar per seconds.
Very good, 1 over molar seconds. Okay, very good. Here's another one. Now I'm going to leave this one up to the folks at home. Let's let everybody go and push pause and go try this. Try to find out what the order of the reaction is with respect to NO2. And yeah, go for it.
Okay, here I go. Push and pause. There we go.
All right, did you get to do it? Did you try it out?
Yeah, I got it.
Okay, so what did you do?
Well, I compared experiment 1 to experiment 2.
All right, and what changes in those two experiments?
We doubled the concentration of NO2.
Very good. We double the concentration of NO2. And how does that change the rate?
It doubles it.
All right, so what does that mean the order of the reaction with respect to NO2 is?
It's just 1.
Very good. It's 1. The exponent on that reaction will be, on that reactant concentration will be 1. Excellent job. Okay, so here's another question. Chlorine dioxide is a reddish-yellow gas that is soluble in water. In basic solutions, it dissolves to form the chlorite and hypochlorite. Let's see, chlorite and chlorate, and hypochlorite ions. All right, so the rate law for this chemical reaction, all right, the given concentrations, and at these concentrations, the reaction rate is 0.0248, and we want to know what's the rate constant, which is the K in here.
Well, can we just plug it in?
That's right, we can. So we put 0.06 into here, square it, put 0.03 into here, multiply it by 0.06 squared, and then we have our rate over here, 0.0248, divide by 0.06 squared and 0.03, and that should be our K value. All right, so let's try that. On the left, we got 0.0248, and we're going to divide that by, I'll take this over there first, 0.03, and then we can divide by 0.06 twice. All right, so we get 230. All right. Oh, look, they're all 230. So what's the difference between them?
Oh, they have different units.
Okay. Can we tell which one of these would be the right K by the units?
I'm not sure. How would we do this?
Well, rate. What is the units for the rate always?
Oh, yeah, molar per time, so molar per seconds.
That's for the rate. So that's not for the K, but that's what the rate is going to be. So what units does K have to have so that the constant, or the units over here, times the units for K equals molar per second?
Let's see. Over on the right, you got molar squared times molar, so molar cubed altogether.
That's right, and you only want molar per second over here.
So it's going to be 1 over molar squared seconds. So it's, oh, it's none of those.
That's right, it's none of those. It's this one over here. Very good. So it's 230 molar per molar squared seconds. Okay, very good. That's a good place to stop.